Hello guys, so you're welcome to our next lecture here. So far we have looked at what binary operations are. Okay, we have we defined what a binary operation is. It's basically, if you like, start here as a function from this Cartesian product. All right, S and S to a set S. So you have a set S, you take, if you like, two elements from the set S. So you have A, B here, and you perform an operation, this operation star on them. And then we represent this as, if you like, A star B. All right. The star there could be addition, multiplication, division, subtraction, or something else. We'll look at that in the next few sections. It doesn't have to be any of those, okay? But star here is a binary operation on the set S. If I pick two elements, A and B, okay, A and B are in S. A, B are elements of S. I pick these two elements, A, B in S. If I do A star B, I perform the operation on them, and the result is in S. Then star is a binary operation, okay? Binary operation. So that is important. Take note of that, okay? So that is a binary operation. All right? Otherwise, star is not a binary operation. If I take two elements in the sets, let's say X and Y, and I go X star Y, and I get an answer which is not in the set S, then star is not a binary operation on S. Okay, that's what we learned. And then we'll learn the concept of closure. Okay, closure, or what it means for a subset. If I have a set S and I take a subset H of S, what does it mean for this subset to be closed under the operation star? What it means is that if I take any two elements in H here, the subset, okay, so A and B are in the subset H. If I do A star B, all right, if I operate on this and the element, the result I get is still in H, then I can say that H is closed, the subset is closed under the operation star. Okay, so that's what we've looked at so far. And of course, some examples of these concepts. Okay, great. Now, so far, what we've done is we've encountered binary operations that are familiar to us, like addition, multiplication, and so on. But the goal of abstract algebra is to abstract, all right, some of the basic notions, right, structural notions from these usual elementary algebraic operations, right? We want to abstract, we want to extend them, we want to generalize them, okay? So there are some examples here that will give you an idea of what it means by the concept of abstraction, right? Abstraction from a familiar concept to an unfamiliar concept, okay? So for instance, we know addition, multiplication. What do we mean? We want to generalize those operations or, you know, abstract them, all right, to give us new operations. So here's an example, for instance, right? You want to define the operation star on a set of positive integers by this, right? This is how we define it, okay? This whole sentence is a definition, so keep note, all right? So S star B here is equal to the smaller of A and B, or the common value if A is equal to B, okay? So I'm defining this operation. It's not addition, it's not multiplication, but I'm defining it to be, if I take two elements, A and B, and I operate on them, then my result will be, I'm going to take the smaller of the two. Or if they are equal, of course, I just pick one of them. Okay, so that is the definition of this operation here. So it means that if I have 3 star 10, for instance, both of them, remember, note that both of them are in this set of positive integers. If I do A star B, I pick the smaller of the two. So I get, my answer is 3. If I do 11 star 5, I pick the smaller one, I get 5. If 7 times 7 star 7, I get a 7. Okay, so that is how I defined my operation, or I defined this operation. And all it does is that if you have two elements operating, you just pick the smaller of the two. Of course, you can think of an application of this, right? So for instance, if you go to, suppose you enter the ninth market or any shop, right? Store to buy bread. You find two identically sized breads, right? Same size. One of them is stamped 4.5 Ghana cedis, the other is 6 cedis. Well, which one are you going to pick? All right, you're going to pick the smaller of the two. All right. Why? Because at some point in your life, or somebody taught you that pick the cheapest one, right? Or try and save money. Okay, right? Bend down boutique, right? So pick the cheapest one. So you grab the 4.5 CDs one and leave the 6 CD one for maybe the rich guys. Okay, so knowingly or unknowingly, you are probably applying this operation here. You have A star B. I have two elements. I pick the smallest. I pick the minimum one. So that is like a trivial application of that. Now you can also define it separate. You can define it separately. So define the operation star prime, for instance, on a set of positive integers by this. So if I have A star prime B, I pick A, right? What it means is that I'm just going to pick the first element always. So 2 star prime 5, I pick the answer is 2. 11 star prime 5 is 11. 3 star prime 3 is 3. Okay. So I just picked the first one. And this is from the concept of our knowledge of order, right? If I have two tens, this operation says just pick the first one. All right. There are some things you have to do first. Okay. So put on your socks before you put on your shoes. You have to do that first. Don't put the cart before the horse. All right. Don't put on your shirt before your singlet. Okay. So this operation says pick the first one. And it's neither addition, nor multiplication, nor division or subtraction. It is an abstract operation, a binary operation. Okay. Good. Here's another one. You can also define an operation like this. Prime, star prime prime, right? On the set of positive integers by this. So this is how we define it. We say A star prime prime B is equal to A star B plus 2. Where this star here, this one here is the one I defined in the example 18, where I pick the minimum of the two, or the smaller, right, of the two. Okay. So if I have the operation A star prime prime B, what it means is that I'm going to pick the smaller of these two and I add 2 to it. Okay. So pay attention to these examples that will come back later on. So where star here is defined already. So that means that 3 star prime prime 7, right? I pick the smallest of them, which is 3, right? And I add 2. So that gives me what? 5. If I do this, I pick the smaller one, that's 7, I add 2 to it, I get 9. Pick the smallest, well, they're the same, so I pick one of them and I add 2, I get 6. Okay, so you see that this is an abstract concept. It's not multiplication, it's not addition per se, right? So, but it's a binary operation because my answer here, the results here, I still are positive integers. So it is a binary operation. Okay, great. Good. Now, take note of this. In some of these operations, you will notice something interesting, right? So in the example where we pick the minimum and where we pick the first one, well, we demonstrate that a binary operation may or may not depend on the order in which you perform the operations, right? So sometimes if I do A and B, my answer could be A. If I do A and B, my answer could be B, right? Sometimes they are equal, sometimes they are not. Okay, so from example 19, right? This guy here, where we pick the first one, right? You notice that if I do A star prime 11, I just pick the first one, I get what? 10. So A operation 11 gives you 10. If I do 11 operation 10, I get 11 because I'm just picking the first one. So 10 and 11 and 11 and 10 gives me different answers. So A star B and B star A do not always give you the same answer, okay? When they do, you say that the operation is commutative. So I'll define that later on, okay? But know that the order is important and the result is not always equal, okay? So we'll look at these ideas later on in the definition of commutativity and also associativity, all right? Okay, so commutativity is here. If star is a binary operation on a set S, then star is called commutative. If A star B is equal to B star A for all A, B in S. Again, for all. I said before that pay attention to definitions. So it must hold for every pair that I pick. This must hold. If that is the case, then you say that star, the operation star, is commutative. Okay? The if here could have been if and only if. In other words, if this is true, then star is commutative. And if star is commutative, then this must hold. Okay? So in a definition, if you see if, it's always interpreted as if and only if. But it's not the same for definitions. I mean theorems, sorry. In the case of a theorem, it has to be specifically spelled out that you have an if and only if statement. But in the case of definition, when you see if, it's the same as if and only if. Okay? Good. Now, for a binary operation, remember that so far, what we've been doing is that we just pick two elements and then we combine them, right, using the binary operation. The question is that, what do you do if you have three or more operations? Three or more, let's say, elements, I should say, right? So if I pick A, B, and C from a set S, and I have A star B star C, how do I compute this? All right. Do I do A, B first, or do I do B, C first? Of course, these are the two ways you can do it. You can do A, B first, the result, you operate it on C, or you can do this. But the two approaches are not always the same. They don't always yield the same answer, okay? So it's important to know when the answers will be the same, okay? So we want to capture all of these notion in the definition of associativity. We'll come to that. So, but let's look at some example to illustrate this. For example, the star that we looked at already, where if I have A and B, I pick the smaller of them, right? We've seen the example 18. If you take that example, then if I have 3, 4, and 11, for instance, and I do 3 star 4 star 11, and I do the 3 star 4 first, well, I pick the minimum, I get 3 star 11, I get 3, right? Here, I pick the minimum, I get a 4, operate it with the 3 here, I get 3. So in this case, I get the same answer, whichever way I do it, okay? Which means that A star B in brackets star C is equal to A star in brackets B star C, okay? When that happens, we say that the operation star is associative, okay? It is associative, okay? The point is that if I know that it is associative, then I don't have to worry the combination that I do first. It doesn't matter whether I compute BC first or I do AB first, you see? So that is why it is important to know whether an operation is associative or not, okay? To remove any ambiguity in your computations. All right. Now, on the other hand, if you look at this example here, where we define it to be A star B, in other words, you pick the minimum and add 2 to it, right? If you consider that operation, then you will notice this. If I do the same example like this one I did before, you realize that 3 star prime prime 4 star prime prime 11. If I do this first, I pick the minimum and I add 2, right? The smallest is 3 plus 2 is 5. So I have 5 and I operate it on 11. The smallest again is 5 and I add what? 2 to it and I get 7. So if I do this, I get 7. What of this? If I do the 4 and 11 first, okay? I think I get a minimum here, which is a 4. I add 2 to it, I get 6. So I have 3 star prime prime 6. Take the smallest one, which is 3, and add 2, you get a 5. okay? By this, I'm going by this. You get 5. So the two are not the same. This one gives you 7, this one gives you 11, okay? So in this case, this operation does not need to be equal to that. They could be different, okay? But when they are equal, then you say that it is associative. So the following definition helps us to differentiate the two cases, whether it is associative or not. So if a binary operation star, all right, on a set S is such that A star in brackets B star B is equal to A star in brackets B star C, if this is equal for all A, B, C, and S, then we say that the operation star is associative, okay? So that is important. And also note that A, B, and C do not have to be distinct, okay? They could be the same numbers, or this and this could be the same, all right? But this operation must still hold, okay? They don't have to be distinct. Okay, great. I have made this point already. Okay, so here is a simple example. Subtraction here on the set of integers is neither commutative nor associative. Okay, why is that? Okay, we can just pick a few examples to show this, right? Now, if I pick two integers, 1 and 2, for instance, the operation is subtraction. If I take 1 minus 2, I get -1. If I take 2 minus 1, I get +1. They are not the same. Therefore, subtraction is not commutative under a set of integers, okay? It is not commutative either. If I take 1, 2, 3, all right, and I take 1 minus 2 minus 3, and I do this first, okay? Let me see if I can pull my, let me get my, okay, I'll probably just use the comment here, okay, to write this out, okay? So here, all right, so if I do 1 minus 2, I get -1. -1 minus 3, that gives you -4, right? And if you do 2 minus 3, that is -1. 1 minus -1 is 2. This gives you +2. They are not equal. You see that? So on the left-hand side, you have a -4. On the right-hand side, you have a +2. So because they are not equal, subtraction is not associative under the set of integers, okay? What of this one? This is A star B. This is how we define this operation here. This star here is defined by this. So this operation star is 2 times A plus B, all right? So we define this operation under the set of integers. We want to know whether it is commutative or associative or both, all right? Okay, now it is commutative. We can show it, right? That's because if I take B star A, right, I'm going to have, following this operation, I'm going to have 2, right? You take the first element and add to the second one. So 2 times B plus A, okay? But we know that addition, this is elementary addition. Addition is commutative. So we can actually switch this from the elementary algebra that we know, right? So this is the same as 2 times A plus B, but 2 times this thing, right? This whole thing here is the same as A star B. Okay, so this is A star B. What it means is that A star B is equal to B star A. Therefore, this operation here under the set of integers is commutative. Okay, all right, good. So we have commutativity sorted out for this operation under this set. Now it is not associative. This operation is not, and we can prove it using just a single example. Okay, or disprove it, I should say. We can prove that it is not associative, okay? So I pick 2 elements, 0 and 1, all right? And I do 0 star 0 and star 1. Well, following this rule here, this operation here, 0 star 0, what I do is I add the 2 and multiply by 2. So 0 plus 0 is 0, multiply by 2, you get 0. So I'm going to take 0 and star it with 1. Well, I'll take 0 plus 1, that is 1. If I multiply by 2, I get 2. So this gives me 2. Well, if I do this operation next, right? If instead of doing 0, 0 first, I do 0 and 1 first. If I do 0 and 1, following this, I'll take 0 plus 1. Okay, that is 1, and I multiply by 2, I get 2. So the next I'm going to have, well, let me just do this, right? So the next, so this is a 0 star. This guy here gives me what? 2. So if I now do 0 star 2, I'm going to have 0 plus 2, which is 2. If we multiply by 2, I'm going to get 4. That is why we have 4 here. See? So in this case, it is commutative, but it is not associative because I pick 2 integers, 0 and 1, and perform these operations, and they are not equal. Therefore, star is not associative under the set of integers. All right, great. So let me get rid of this. I don't have to. Let's go back to full screen mode. Oh, I need to move away from this thing. I've seen this before. And then we can go into full view. Okay, good. Great. So here we look at, so we are done with the concept of commutativity and associativity. Our next line of action is to show that, let me see. Why does it feel like, oh, no, that's fine. So the next line of action is to show that, we can actually represent binary operations using tables. Okay, that is what I want to do next. So we can use tables to demonstrate binary operations on finite set. So if I have a finite set, so far usually we'll be looking at infinite set, like a set of integers is infinite instead of real numbers. But if I just take a finite set, a set of numbers 1, 2, 3, or ABC or ABCD, finite set, you can actually use a table to show how the elements you operate on them based on some rule, right? If you're giving the rule or if you're giving the table, you should know how operations are performed, all right, on them. So often this is what we do. So I will show you. So for example, you define the operation star on the set S, right? The set S has elements A, B, and C. What you do is that you take the ith entry on the left-hand side of the table. Let's go here. So you have star. You label all the elements on the table on the top here, and then on the right, on the left side, you label them this way, right, from top to bottom. So ABC this way. Okay. So for this table, well, some rule was using it. We are not giving the rule. Okay. A rule is given, but what this means is that if I take A star, if I take A star A, I get B. All right. If I operate A and B, I get C. A and C, I get B. All right. If I take B and A, I get A. B and B gives me C. B star C gives me B. Okay. So that is how you operate. When you have a table, that is how you perform binary operations on them. All right. Now, in this case, we can show that this operation here is not commutative. Why? So we can easily do that here. Let me, should I pull my, okay, I'll use the, let me just use the comment again, comment thing here. Let's use this. So here, why is it not commutative? Let's take, let's take for instance, A and B. If I do A star B, what do I get? A star B gives me C, right? For it to be commutative, B star A must give me the same thing, right? But if I do B star A, I take B star A, what does it give me? It gives me A. So, and these two are not equal, right? These guys are not equal. So A star B is not equal to B star A. So from the table, I can tell that the operation star is not commutative. All right. And this single example is enough to make that statement. Okay. Good. If it was commutative, this is what we should expect, right? I would let me pull out. So let me get rid of this and just do another one here. Suppose star was commutative, then what do we expect? If it was commutative, you would expect that here. So let's do this. A, B, C, A, B, C, right? The star is here. This is how we do it. Okay. All right, great. Now, A and A, that's okay. So let's put a B there. B and B, we are not concerned about that. C and C is A here. So that's okay. Good. Now, if the operation was commutative, okay, I do A and B, this gives me C, okay? I expect that if I do BA, I should get C as well. You see, A and B, C, B and A should also give me C. All right. Now, A and C, AC gives B. I also expect that if I do CA, I should get B. So C and A should also give me B. All right. Here, I have BC. BC gives me B. BC gives me B. All right. CB. C and B must also give me B. So suppose that this star, this operation here was commutative. If it's commutative, this is what we expect to see in the table. Now notice a few things here. Notice that because this is commutative, if we take this diagonal, oops, let's see, here. Okay, so take this, notice that along this diagonal or across it, you will notice that the elements are symmetric. Okay, across this diagonal, B, I have B here. Across it, I have a B too. This is C. Across from it, B and a B, C and a C. So if the operation is commutative, what you expected is that you expect symmetry across this diagonal here. Okay, if I take this element and if I cross this diagonal, I should get the same element. If I take this and I cross the diagonal, I should get the same thing. Okay, so that is what you expect for a commutative operation in a table. Okay, so basically this is just to introduce you to how you use tables to do binary operations. Okay, given a table, you can be asked to do different things. For instance, I can ask you, for instance, find A star B star C. What do you get? Okay, of course, you do AB first. What do you have? AB gives you C, and you have to take that C and operate on C. C and C gives us what? A. So you should get what? You should get A as your answer. Okay. All right, good. So that brings us to the end of binary operations in general, right? Binary operations. We looked at binary operations. We looked at closure, all right? We looked at some examples of that. We looked at what it means for an operation, a binary operation, to be commutative, what it means to be associative. All right. So go over some exercises. I have some exercises here. You can go over them. Again, let me exit from this comment section here and see the full view. Okay. So once again, you should, you can try your hands on some of these exercises. Okay. So try your hands on some of them. Yeah, basically based on the things you have done already. This is a table that you have seen. It's another table that you can fill. Table, define this on this. Determine whether the binary operation defined is commutative and whether it is associative. All right. So is defined. So pick elements from the set and see whether it's commutative. So try your hands on some of these exercises. Let me see. Okay. So you should be able to do that. Okay. All right. Okay. So I will end this video here. Is I think almost about 30 minutes. So that's fine. In the next video, we'll go into groups, right? I'll give an introduction to what to groups, and then we'll define what a group is. So we'll look at some examples of groups. So that's what we're going to do in there. I'll be doing in the next video. All right. Okay, good.